In this video, I'm going to show you guys how to use the EQ mathematical relationships and the equilibrium equation that includes energy transfer between more than one object or system. It is important that you probably pause the video and try these problems on your own before just simply watching me work through them, and then you can replay the video to see how your work compares to mine. So in this first problem, I want you guys to think about is imagine an unidentified metal with a mass of 250 grams that was heated to a temperature of 100 degrees Celsius, but then it was allowed to cool to 22 degrees Celsius. And while it cooled, it released 2,145 joules of energy. We don't know what this metal is, but we can use the specific heat value in the future to determine and estimate what this metal is. So we need to solve for the specific heat, and that variable in our equations is identified as the C in any of these relationships over here. Now you guys got to decide which relationship you're going to use, as they can be overwhelming. The top two equations or relationships have to do if you're simply solving for EQ at some temperature, at some moment in time. The equation below has the change in symbol. So this is if there's been a change in temperature due to some kind of transfer for just one system or one object. The ones that are located below equal to zero are the equilibrium thermal equations that help you predict interactions between more than one interaction between two different objects or systems. In this case, this problem sounds like there's a change in temperature going on between just one object. So we're going to use the change in EQ equation because it has the change in temp and it doesn't really account for any other object or system we're going to involve with. So I'm simply going to plug in the mass, the change in temp, and the energy that was released for the change in EQ and rearrange it for the C value. So I already know that the release suggests a transfer out of a system. So really this should be a negative 2,145 joules. So I'm going to do negative 2,145 joules of energy, and I'm going to set it equal to the mass, which is 250 grams, times C, which we do not know yet, and the change in temperature you guys can figure out on your own if you pause the video and have worked on this on your own. You have the option to either put this into Celsius or Kelvin. The reason why it doesn't matter whenever there's a change in temp, because historically 1 degree of Celsius change is equal to 1 Kelvin change. So it doesn't matter here. I'm simply going to do mine in Kelvin, and then I'm going to use the change in the variable spot where the change in temp is. So if you add 273 to the 22 degrees Celsius and you add 273 to the 100 degrees Celsius and you do the final minus the initial, you should do and see that even when you do the Celsius version, it'll be the same change in temp. So I stacked my final temperature at 295 because the metal has decreased temp. It's going to be less. And then the initial temp at 373 Kelvin, and that's more because of the whole process of it cooling down. So if I subtract those two, I should get a negative 22 Kelvin. And if you did this with the Celsius, you'll see the same thing when you take and subtract the 22 degrees Celsius from the 100 degrees Celsius. Actually, that's wrong. It's not negative 22. It's going to be negative 78 Kelvin change, or negative 78 Celsius change. So for the change in temp from the mathematical relationship we're going to use right here, I'm going to plug in the negative 78K. Now the next thing to do is to start working on isolating the C variable. I'm going to take the negative 78 times the 250 grams and rewrite my relationship. When I multiply the 250 grams times the negative 78 Kelvin change in, I get 19,500 grams Kelvin. And again, these units could be Celsius if you did the change in with Celsius. And then I'm going to bring down the C variable. Now in other classes you might have experienced solving for variables. When you've got a quantity like the 19,500 connected to the C variable through multiplication, most students will say to just simply divide that out, and that's what we're going to do. And then that cancels it. And leaving the relationship unbalanced, I'm going to divide it the other side by the same value. And that should be negative 19,000 also because of the negative 78. And what's great about this is that no units on the left cancel. There's joules for every gram Kelvin, which are the units for specific heat capacity. So now we got to just simplify and divide those out. Our C value is going to be 0.11 joules for every gram Kelvin, or you could mark that as Celsius. And anyone could look that up on the internet and try to estimate what metal this likely is. I'm going to reset for another problem. I recommend that the next problem you try on your own before just simply copying down or watching what I do. This next problem is a two-part problem. I'm going to try to do part 1 and part 2 in this video. Part 1, we're going to read the directions here and determine the final temperature of the gold and water after they have reached equilibrium. So what you guys need to imagine is that if you've got a chunk of gold at some temperature and we're going to put it in a container of water and measure the temperature change that the gold does to the water, and we're going to end up using that to predict the final temp they end up with. So if you continue reading, it says imagine a 100-gram sample of gold that has initially been heated to 300 degrees Celsius. And again, we've given you the specific heat of gold at 0.13 joules for every gram Celsius. The gold is placed in a metal cup that contains 150 milliliters of water. Now, without doing a unimultiplier, most people know the density of water is 1 gram for every 1 milliliter. So I can simply identify this as grams of water. And that water is at about room temp, which is 22 degrees Celsius, and has a specific heat capacity of 4.18 joules for every gram Celsius. So because it sounds like there's two objects interact with each other and that energy transfers from high energy to low energy or hot to cold, this sounds like a equilibrium problem where we're trying to find the final temperature that all the objects get to. So I know I can't just do a simple EQ equation. I can't just do a one-off change in EQ because there's two systems involved here. So I'm going to have to do one of these down below that includes the change in temp of one system, the mass and the specific heat, the change in temp of the other system, the specific heat and the mass, and go from there and solve for my final temp. The problem is with this equation here, there's no final temp explicitly shown. You have to do the last equation for equilibrium that has the final temp hidden and substituted in. So we're going to have to use this version. Again, if I were you, I'd pause the video, plug in the important information, and try to solve for the TF by yourself. Now in this video, I can also do it in Celsius or Kelvin because it's a change in temperature style equation. And the change in for Celsius and Kelvin is still the same amount of change. 1 degree of Kelvin is 1 degree of Celsius. So I'm going to start my work and do the gold first. I'm going to plug in the mass, specific heat, the mass, specific heat, and then I'm going to fill in the temp final minus temp initial using Celsius. The specific heat capacity of gold is approximately 0.13 joules for every gram Celsius. I don't know temp final, so we're going to do a little substitution. Temp initial is 300 degrees Celsius. Again, if the problem specified doing it in Kelvin, you would want to change these to Kelvin. And now I'm going to do the change in EQ part for the water, which is at 150 grams and a specific heat capacity of 4.18 joules for every gram degree Celsius. And again, they're both going to reach the same final temp once the gold has transferred its energy to the cooler water. At some point they'll reach some common temperature and have equilibrium momentarily. That's the final temperature we want to try to get. And the initial temp of the water is at 22 degrees Celsius. So the next step you guys got to think about is, what can I do to start making this simplified? A lot of people will argue they're just going to go right in here and deal with these parentheses, but the variable is hidden inside these. So I'm actually going to tell you guys to start with the outside and start simplifying this multiplication product out on the leading side on the left here and on the left of the water package, and then rewrite it. So if you take 100 times the 0.13, you guys should get the grams canceling, and you should get 13 joules for every degree Celsius. And then you got to take and bring down the TF minus 300 still. And now let's do the 150 times the 4.18. And when I did this, I got approximately 627 joules for every degree Celsius. And then we need to bring down the package of the change in temp. And now you guys have a simple term out front of the parentheses, the 13 joules for every degree Celsius, and on the other package we have 627 joules for every degree Celsius. Now, most students will obviously say that it's time to distribute into the parentheses, and that's fine. So if you like to draw arrows, you can. If you don't like to, you don't have to. So if you take 13 joules for every degree Celsius times TF, it simply becomes 13 joules for every degree Celsius. And now TF is stuck to it through multiplication. If you take 13 times the negative 300, you should get approximately negative 3,900 joules, because the Celsius technically cancels the Celsius out. Now if you distribute the 627 inside the TF, you should have 627 joules degrees Celsius times TF, now stuck together as a package. And then furthermore, if you take the 627 joules for every gram degree Celsius, or excuse me, joules for every Celsius times the negative 22 Celsius, the Celsiuses will cancel out and you're only left with joules at this point. And if you take 627 times the negative 22, you should get approximately 13,794. Again, if you didn't pause the work and try it on your own, pause it and try these steps on your own before I get further along. Now that we've done the distribution, it's time to look for like terms. For teaching purposes, I like to underline the like terms just to draw attention that this quantity has a joules degrees Celsius stuck to a temp final, and so does this one for the 627. So those two can be added together. This negative 3,000 joules is similar units to the negative 13,000 joules on this side. So if we add those up and simplify it, we should end up with 640 joules Celsius times that TF still. And then if we subtract the 13,794 from the negative 3,900 joules, we should get approximately 17,694 joules. Now this is starting to look very familiar to people as a similar like y equals mx plus b, where we have this variable out or embedded with multiplication to this quantity of 640, and then this tail end standalone 17,000. So our goal is to get TF by itself. I'm going to start with dealing with the 17,000 and adding 17,000. Doing that cancels it out, but I've just manipulated the right side, so now I need to bring that over to the other side. I'm going to bring down what's left over, this package right here. And now TF is stuck to the 640 through multiplication. Most students will say to divide that to cancel out the 640. It cancels out both packages, but you must do it to the other side now. And when you actually write down the 640 joules for every gram Celsius, the joules will cancel out and you're left with Celsius, which is a temperature, which means you've likely set this up correctly. So if you simplify that, you should get a temp final. Once you take the 17,694 divided by the 640, you should see that in Celsius, it's 27.6 degrees Celsius. And if you wanted to know Kelvin, you would simply just kind of cheat and add the 273 onto that.